Hi everybody, my name is Konstantin Klamka and today I will present Rapid Iron-On user interfaces. This project is joint work with Raimund Dachselt from the Interactive Media Lab at the Technische Universität Dresden and Jürgen Steimle from the HDI Lab at Saarland University. So let us start with the emerging trend of e-textiles. Recent advances in functional textiles and electronic miniaturization are bringing new generation of wearable user interfaces that are deeply integrated into our clothing. Further applications can be found in the fields of fashion, smart workwear, medical applications, active sportwear, and accessories. But a remaining question here is how technology enthusiastic makers and innovative designers could take part in this development. While makers have great technical skills and the capabilities to innovate and prototype, they often use manual sewing techniques. However, the manual fabrication on the yarn level is quite time-consuming and cumbersome. In addition, textile and fashion designers require wearable prototyping toolkits for early design stages, but they commonly do not have access to expert machinery. These kind of machines are typically outside the realm of a prototyping space. By looking at emerging materials like conductive or resistive fabrics, as well as the continuous progress in flexible and printed electronics, we thought about how can we develop an easy and sketching-like fabrication approach. Inspired by the sketching-like interaction of handheld correction tape or packaging tape dispenser, we introduce Rapid Iron-On user interfaces, a novel fabrication technique to combine design and fabrication into a single process. Therefore, we developed a handheld ironing tool that directly transfers adhesive functional tapes and patches onto fabrics. The device uses an iron that could be pushed for bonding tapes via heat activation. The tapes itself are rolled on spools with a carrier layer. As you can see in the video, it is possible to iron on traces in a sketching-like fashion. Further, we looked at several components that could be ironed and introduced a comprehensive library of components. To demonstrate the versatility of our toolkit, we also implemented applications for ubiquitous and wearable computing. Finally, we conducted technical experiments as well as expert reviews. But before I go into details, I will briefly position our work in the context of prior research. So if we look at crafting techniques, Beakley and colleagues pioneered the LilyPad platform that allows to connect electronics with conductive yarns and laser-cut fabrics. In addition, Kit of No Parts introduces an approach of crafting electronics, rather than designing discrete components. Schnittmuster discusses a meta toolkit. In contrast, ready-made toolkits allow prototyping with prefabricated components. Research like iCatch, MakerWare, and BodyHub build on the idea of customizable, body-worn building blocks. Finally, Z-Badges enable resistive and capacitive sensing and can be ironed onto textiles. Furthermore, projects like Jacquard demonstrate how smart textiles could be produced at a large scale. SmartSleeve and Resi introduce on-clothing interaction based on resistive sensing matrices. Soft inject circuits demonstrates how multi-material inkjet printing enables circuits on a variety of substrates, including iron-on textile films. Since our work is inspired by cuttable smart tapes, we also looked into this research. While shape tape and sensor tape capture its deformation, touch tape allowed to sense a hand's position. Armor tapes are commercially available, high conductive and stretchable textile ribbons. Finally, research has been done in interactive fabrication and construction. Most related to our work is Sketch and Stitch, that combines the design of components by sketching and the fabrication by using an automated embroidery machine. Let's get back to our Rapid Iron-On tools and see how the ironing process works in detail. The first thing I want to talk about is the way how we constructed the material spools. The iron-on material stack basically consists of 3 layers: a carrier layer, a functional layer, and an adhesive layer. The first layer serves us as a carrier for all iron-on spools and is made of heat-resistive baking paper that we coated with sticky glue. The most important part of our spools is a function layer that consists of materials like ultra-thin conductive fabrics. Most spool materials are fabricated with a vinyl or laser cutter, but as we will see later, it is also possible to integrate rollable, printed, electronic or sandwich materials. The last adhesive layer is made of fusible web that is bonded with the functional layer. We transferred all designs to the carrier layer and rolled it onto spools. But what can we do with the Rapid Iron-On tool? Let us start by looking at the fabrication of traces and circuits. Working with traces and circuits had to support multiple actions, including creating, connecting, bridging, or deleting traces. On the other side, they require special properties like a good connectivity, an easy arrangement, and special shielding, stretchable and multi-layer properties. Wow, this is a lot, but let us see how we can tackle these challenges with the Rapid Iron-On approach. We fabricated different trace spools, including standard traces, as well as stretchable ones in different sizes. Standard traces consist of high conductive fabric with a thickness of 110 microns and have a pitch of 1/5 of an inch. To finish the sketching process, the designer can push a button to cut the trace with an actuated blade that we integrated into the tool. In addition, we explore how commercial elastic ribbons can be used with our Rapid Iron-On dispenser tool, as well as design and fabricate our own ultra-thin stretchable trace by combining a horseshoe pattern with high conductive fabrics. Furthermore, we introduce shielded traces that consist of a conductive outer shield and a core trace that is sandwiched by 2 isolation tapes. The whole tape is just 350 microns thick and very flexible. Next, I will briefly describe how traces can be connected. Single-wire traces can be connected quite easily by creating a new one on top that overlaps with an existing one. The great thing here is that connections did not have a negative effect of the overall resistance, as we have shown in technical experiments. Multi-wire traces can be extended in the same direction, but how to realize angles and crossings for multi-wire traces? If a user wants to attach an angled connection to existing traces, a connector stencil could be placed above, ironed on by using our tool in ironing mode, and finalized by peeling off its protection layer. In order to continue the sketching, the designer had to insert a trace spool and check whether the axes move correctly. Next, the user can place and align the tool and continue sketching. As a result, all traces are bridged, building a high conductive connection. But what about reversible connections? Would not it be good to utilize already existing mechanisms, like zippers? Based on our Rapid Iron-On fabrication approach, we introduce a connection zipper that can be used as a multi-trace connector to physically bridge traces. Therefore, the designer can literally iron the traces to the teeth of the zipper. Zip-on connections can be useful as exchangeable mechanisms for multiple purposes, like detaching electronic parts before washing or changing models depending on the context. In addition to the conductive fabric, we also explored how other material spools can be used. For example, for building a custom pressure touch sensing matrix. Therefore, the designer first had to sketch sensing rows, and then change the material spool to piezoelectric fabric and sketch again above. To finalize the sensor, a last trace layer is applied. The result is a custom-shaped 4x4 pressure-sensitive matrix that works via resistive sensing. As composition techniques, our approach supports the arrangement of different spools side by side, and the layering of tapes and patches, as well as the utilization of textile accessories. So far we have learned to manage wiring, right? But what about further input, output and computing components? With our work, we also introduced a comprehensive library of components, which are mostly realized as functional patches to be ironed on in the same manner. Therefore, we explore how the versatility of available flexible components can be made ready to use for the rapid iron-on approach. In the following, I will briefly discuss selected representatives of each class. So as basic touch input, we fabricated ready-to-use capacitive input controls, including buttons and sliders. They can be simply placed and ironed. Furthermore, our library also includes prefabricated pressure and bend sensors that are made of a stack of conductive and piezoelectric fabric. In addition, a designer can place an identification patch, then iron the tag using our rapid iron-on tool, and finally peel off the protection layer. The result is a flexible and strongly connected tag that could be used, for instance, inside a lab coat for access control. But how can we iron more rigid semi-flex electronics like this SMD LED tape? We fabricated different irons with unique cutouts. If we look, for example, at the U-shaped iron, it is possible to avoid contact with the small LEDs and only iron the edges of the tape. This technique allows us to iron on SMD LED tapes. Furthermore, we also have resistive heating patches and tapes. In order to support computing components, we combine flexible solar cells with fusible web to make it iron-able. The tape is cuttable at any position and provide enough power to charge a battery. To see how the toolkit works for real-world applications, we also realized 3 application examples. Our first one is a smart cuff button that acts as a direct and discrete input device, for example for controlling a slide deck during a business presentation. The interactive metal button can be slightly displaced in all directions and snaps back elastically while sensing its position. Technically, we used a capacitive 4-way slider button patch that we ironed under a cuff metal button. Furthermore, we ironed an e-ink display and an NFC tag on a doctor's white coat, providing access and pager notifications. This example demonstrates how advanced electronics can be integrated onto textiles. Finally, we realized an interactive messenger bag with solar tapes at the strap. The bag's inside lights up if somebody opens it. Therefore, we used a band sensor on the LED tape. In addition, we integrated a moisture sensor at the bag's bottom to sense whether a bottle leaks. Finally, a music player control made of capacitive touch widgets is integrated at the shoulder pads. The microcontroller can be zipped off to reuse it in other contexts. So after we've seen the toolkit in action, I would like to talk about 3 expert reviews that we conducted. In order to speak with textile and fashion design experts, we drove to a French design university, physically presented our toolkit and conducted semi-structured interviews. In addition, we also visited a textile machinery research institute in Germany, where we asked a machinery and fiber expert to test and review the rapid iron-on approach in an interactive hands-on session. Each interview took around 60 minutes. The textile and fashion experts state that the iron-on roll and patch approach is in between large-scale production and manual crafting. This makes absolutely sense. However, they have also concerns about adding tapes and patches, since they think that it is important to work from the beginning with the finer materials, to consider the visual and sensory qualities in the whole design process. In addition, the machinery and fiber expert compared the rapid iron-on approach with other e-textile solutions. He stated that the production time, required knowledge, as well as costs are clear advantages. The scope of functionality is comparable, and the durability and the degree of integration is less good. So let us conclude. With our work Rapid Iron-on user interfaces, we presented a novel fabrication approach for interactive textile prototypes that allows to enhance fabrics with rich digital functionalities. Therefore, we developed a handheld ironing tool that directly transfers adhesive functional tapes and patches onto fabrics. With our comprehensive library of components, we demonstrated the technical feasibility and its widespread applicability. We further demonstrate applications for ubiquitous and variable computing and reported findings from expert reviews that identified benefits, limitations, and opportunities for future work. As a next step, we plan to run workshops in design schools and makerspaces to investigate adaptation and usage practice. Thank you for watching our presentation, and if you have any questions, I am happy to answer it via mail. If you're interested in additional resources and building instructions, please check out our project page.